best you can really do in hypothesis testing context is to say that you either have evidence supporting the null hypothesis
Mm.
or you have evidence in opposition to the null hypothesis. So the logic process is to set up two completely mutually exclusive possible outcomes.
Mm.
One of those we call the null hypothesis. A so-called two-tailed version of that would say that we're going to check and see if it's true, set up a null hypothesis, that the population mean really equals 30,
Mm.
even though the sample mean that we have available says 25. The alternate hypothesis would say if the null hypothesis says 30 is the correct answer,
Mm.
the alternate hypothesis would say, no, it's not. And so the null hypothesis would kind of be written as saying mu, the population mean equals 30.
Mm.
And the alternate hypothesis would be written to say it's not equal 30.
Mm.
If the sample result is far enough away from the hypothesized value, the hypothesized population value, then you'd say, well, there's enough evidence here to rule out the possibility 30 might really be the correct number. But as I was saying before, the amount of data that you have available, sample size, has a lot of bearing on. If you have a sample size 10 and you're trying to see whether 25 is different from 30, it's going to be a lot harder because you just, by definition, have less information. If you've got 100 observations, you're a lot more likely because you just have more information, a well-informed decision. So just in general terms, the bigger the sample size, the more likely you are going to be to reject the null hypothesis and to accept the alternate. The logic problem that nearly everybody has with this process is that students, people in general, kind of don't quite understand why you say you fail to reject. Fail to reject to many people means, oh, I accept that. Well, it doesn't. So you only accept something in the context of actually being able to reject a null hypothesis. So when you do a hypothesis test, kind of by definition, you test the null hypothesis. You don't test the alternate. So you test the null hypothesis that the population mean is like 30, and you compare the sample data and the amount of variability within the data, that's a standard error, against that hypothesized population value. And if that difference is kind of large in terms of standard error units, like more than 2 standard errors different, then you would say, okay, I reject the null hypothesis, I accept the alternate. But if you get to a point where you have a difference that's substantially less than 2 standard errors between 25 and 30, that'd be probably in the case of a smaller size sample, then the unfortunate tendency is for people to say, okay, I will now accept the null hypothesis. And I'll say, yeah, 30 is the correct answer. And that's really not correct. So all you can say about the null hypothesis is that you reject it if you get a large number of standard errors of difference, or that you fail to reject the null hypothesis if you don't have a substantial number of standard errors worth of difference. And so that there's this kind of funny asymmetry. You can always reject a null hypothesis with enough data against it, but you can't technically accept it. So you either reject or fail to reject a null hypothesis. Once you say you accept, it means that, okay, whatever that number is, like 30, that's true. And you just simply don't know that. So it all has to do, again, with probabilities, and in this particular context, with the notion of the standard error, which is a measure of, on average, how different is your sample result from the hypothesized population value.
I see.
And to most people, that's illogical.